All right, so last class we were just kind of starting a real brief overview of the different qubit platforms in quantum information science, mostly through the lens of what we'll talk about in the next several weeks of quantum computing. So we talked a little bit about superconducting qubits based on Josephson junctions and trapped ions, where there's lots of different manifestations, and typically you use heavy ions. The third kind of qubit are the spin qubits, and nitrogen vacancies are one such spin qubit, but they've been actually most widely developed in the case of solid-state quantum dots. So these are not the quantum dots that won the Nobel Prize this week. Those are colloidal quantum dots, and we'll talk about those in a minute. So these are mostly made via any number of epitaxial or lithographic methods. One of those is shown here in this diagram. So this is where quantum dots are defined by gates on a two-dimensional structure. So it's just how the gates are arranged that dictate little islands of charge in these two-dimensional materials. You can also make these solid-state quantum dots by lithographic patterning of quantum wells. And the most common way that they're made is actually by this so-called Stransky Kraskow mode of thin film growth, where adsorbate islands form beyond some critical film thickness depending on strain of the growing layers. And so you typically start with substrate and you start growing film, and above a critical threshold, little islands that are nanoscale in dimensions buckle up out of the film, and that's kind of the general way people make these kinds of epitaxial quantum dots. So the one thing that's a big disadvantage in making quantum dots for qubit applications via any of these methods is that the quantum dots are not positioned deterministically, so they're kind of show up in random locations almost, so you can't really dictate exactly where they are. So that's one negative. So the simplest spin qubit based on one of these solid-state quantum dots is an electron spin located inside the quantum dot. And so you can kind of see that in this diagram. You can also obviously use hole spins, but electron spins are the most common. There's different drawbacks to using one electron spin or multiple electron spins or holes. But this is kind of the most generic version. So these spins can act as simple quantum systems in lots of ways, but they also experience really complex effects due to the environment that they find themselves in. And that's a big negative to these systems. But they can be controlled quite easily. So they can be controlled by both magnetic and electric fields, and they can generally be grown pretty straightforwardly, as I mentioned. Different types of spin qubits have different control mechanisms and noise susceptibilities. And the earliest experiments of this type were based on gallium arsenide-based quantum dots. But other types of solid-state quantum dots have also been explored. So gallium arsenide is kind of the most conventional. But also you can create these kinds of quantum dots based on silicon, traditional silicon technologies. Silicon and metal oxides, or even doped silicon, like phosphorus-doped silicon, for example. So traditional N-type doping of silicon, you replace one single silicon atom with a phosphorus atom, and that introduces an extra electron to the valence band, or near the valence band, of the silicon. And so that defect can act as a qubit. So solid-state quantum dots are typically described by this central spin of a single charge, coupled to 10 to the third to 10 to the fifth nuclear spins via some kind of hyperfine interaction. So we have the electron spin is coupled to a large number of nuclear spins. And so this ends up looking a lot like the atomic clock kind of model that we talked about in the first part of the week. The lack of translational motion in these systems provides really long spin lifetime. So the quantum dot is literally quantum confined. It's confined to that small nanometer region. So that's really good. Yeah, lack of translational motion. But that's kind of offset by this interaction of the spin with the complex environment that it finds itself in. So things like electron-phonon interactions and quadrupolar couplings and spin diffusion and impurities in the rest of the semiconductor can really influence the properties of this qubit. And all of those things that I just described apply equally to diamond vacancy centers. So those are just a much newer qubit technology that was discovered in 1997. But these epitaxial quantum dots have been around for a long time and are the foundation of many other traditional optoelectronic technologies. All right, questions about spin qubits? In terms of semiconductor technologies, gallium arsenide is kind of king. So in the photovoltaic universe, gallium arsenide has the highest efficiencies. Its electrons and holes are kind of the most well-behaved. It has very fast carrier diffusion properties. I think just a lot is known about it as a semiconductor. A lot is known about how to make the quantum dots based on really fine control of the film fabrication. All right, so the next kind of qubit technology that we want to talk about is photonic qubits. And in optical systems for quantum processing, the unit of information is the photon. And as we discussed for quantum key distribution, you can encode your information using different properties of light, but polarization state, for example, is a really easy way to do it. Now, the thing that's cool about light as a qubit technology is that photons are very durable, and they don't interact with things very easily. So they don't interact with each other. And so you can easily avoid uncontrolled interactions that destroy the quantum state that you've generated. But to build a quantum computer, you need your qubits to interact with each other. You need to get entangled states. So to build a quantum computer, you need to make the light, the photons, communicate with each other somehow. So the most traditional way to do this is in a technology called linear optical quantum computing. That's schematically shown on the upper left. So this requires the use of material as a mediator to create these entangled states. On the other hand, there's sort of a new version of optical quantum computing that's based not on materials. So I should mention that these materials, in order to mediate these interactions between photons, must themselves be pure single photon sources, and we'll talk a little bit more about that in a second. Right, so the alternative that's kind of coming about, well, I guess, let me stop here for a second. So in these linear optical quantum computers, you sort of have this kind of array of single photon sources in cavities on the left-hand side, and then there's this complex network of interactions created in a rich photonic landscape here. So lots of optical processors to do your computation, and then at the end you have single photon detectors to read out the result of your computation. Those systems are usually pretty large in size, pretty complex, and so Xanadu is a startup company that kind of set out to do optical quantum computing a different way, and you can see one of their optical chips that they use for this, and it's sitting on someone's finger. That's very small. So those are the ridges of someone's finger. And so this is a photonic quantum computing chip. They're a Canadian-based company, and they're not using single photons and single photon sources. Instead, they're using squeezed light. They bring light together into these very specific optical systems. They generate these squeezed states of light that they can entangle, and then those entangled states go through the rest of the chip. and get measured at the end. It's a very kind of interesting and innovative way to do this, very different than how most people are approaching this. They've had some really nice demonstrations of the practicality of this approach, which is pretty cool. But I want to talk for the next couple of slides about the more conventional version of this that's based on single photons. And so the idea of single photon generation, so you need a material that's going to couple the light in your optical quantum computer, and it needs to itself generate pure single photons. And so a pure single photon source is this kind of two-state emitter. So it has two clean states, a ground state and an excited state, and it generates single photons on demand. And the way you measure whether you have a single photon source is to do this experiment that's shown here in the top right. This is a Hanbury-Brown-Twiss interferometry experiment. And it's a really simple experiment. So you have what you think is a single photon source. You pump it and it starts generating light. You have a beam splitter right there that's kind of creating two paths to detectors. And then you're just going to count coincidences at those detectors. And at zero delay time on your photon counter up there in the upper right, a pure single photon source will have a coincidence of 0. So the reading on this plot, which is a conventional G2T plot, it's just a coincidence plot, when you have a single photon source at 0 delay, you should have 0 coincidences. In the real world, this is real data, but in the real world, typically we say that if something has coincidence counts at G2 of 0 less than 0.5, then it's a single photon source. But the best ones have G2 0 pretty close to 0. So the question is, what are examples of true two-state emitters? And one of those is colloidal quantum dots. And that's what won the Nobel Prize this week. And it won the Nobel Prize was for the discovery and synthesis of these quantum dots. And so they were first discovered by Alexei Ekimov, who's the guy on the right here, in glass matrices. So he heated up cadmium and chalcogen precursors in glasses and showed that as the glass cooled, he could get this rainbow of yellow, orange, and red related to the size of the different cadmium chalcogenide particles that he made. So that was the first observation of quantum confined semiconductor nanoparticles in like 1981. And then around the same time, either the same year or a few months later, Lou Bruce, who's in the middle, discovered at Bell Labs that this could be done in solution. So you could take cadmium and chalcogen precursors in solution, heat them up, and you could make crystallites of the cadmium chalcogenide that had band gaps that were much larger than the bulk. And he described that as being a manifestation of quantum confinement. He wrote the Bruce equation that is basically just a particle in a box model. And so he was sort of the second discoverer of them. And then the second part of the Nobel Prize is the synthesis of quantum dots. These two guys obviously made them, but they didn't make them well. Because the properties of these colloidal quantum dots and epitaxial quantum dots are related to the size, in order for these things to be useful, they need to be all exactly the same size. So if you're making them in solution, typically when you grow crystals in solution, you make lots of different sizes. So you have to exquisitely control nucleation, which is the moment the crystals are born, so they can all grow at the same rate, so that they can all become the same size. And that's what Muji Bawendi did, who's on the left. He was a postdoc in Lou Bruce's lab, and one of his early papers out of his independent career at MIT was this famous Bawendi hot injection synthesis of quantum dots that all of us in the field show in every talk we ever give, everywhere. Related to this talk is a very recent discovery from Muji's lab. So this is a science paper that was published in 2019 that I think anybody that's thinking about quantum dots as single photon sources has read, certainly has read this paper. And so what you're looking at are light emission properties of individual lead halide perovskite quantum dots. On the left, you see individual traces of photoluminescence from a single quantum dot, just showing that it's constant and steady over time, meaning it's not dying and it's not turning off and on. And then in the middle there, you see an example of one of these G2T measurements. So in the one on the bottom, which has the 0 phonon line filtered, you see that the coincidence counts at 0 are 0. So this is a very good single photon source. And there's other criterion that make something a good single photon source related to the lifetime of the emitter and the coherence time versus that lifetime. And so what they did in this plot is measure the lifetime, the radiative lifetime of individual quantum dots. You can see that they're like 270 picoseconds. They're pretty mono-exponential, meaning they just have one pathway for recombination. And then they went ahead and measured the coherence time for their single photons, and they saw that they're pretty long. They're like 80 picoseconds. Typically, if you have something with a coherence time that's about where the radiative lifetime is about 2 times the coherence time, that's going to be a really good system for single photon emission. And so this was a pretty game-changing paper. This is not what he won the Nobel Prize for at all, but it's a good paper too. Okay, so single photon emitters are really important for optical quantum computing. And the thing that colloidal quantum dots have as an advantage over traditional quantum dots, so the epitaxial quantum dots are also widely used in these optical quantum computers. But the thing is, for optical quantum computing, you need to be able to put your quantum dot into a cavity, and you need one quantum dot in every cavity. And you can't deterministically place epitaxial quantum dot. So colloidal quantum dots, there's ways to process them so that you can, from solutions, so that you can put one in a cavity. All right, questions about optical quantum computing? We will talk a lot about that. There's kind of an intrinsic relationship that relates the lifetime and the coherence time that we want to obey. Ideally, you would want your coherence time to be as long as possible, but that's really, that would be really hard. Yeah, so this is really good. Yeah, so they all vary. These are longer. And some of the ion trap systems, those can last milliseconds. So, right, all qubits have their pluses and minuses. Some pluses are lifetime, and some minuses are decoherence rates. So everything has trade-offs, for sure. Because you're doing your manipulation in these systems with light, which is really fast, the lifetimes don't have to be super long. And what's cool about this is these kinds of systems can operate at room temperature and still have coherence times like this, which is pretty cool. All right, the last type of qubit that we want to mention is the most theoretical. There's no real demonstration of this. There's lots of theory about it. There's people that have sort of claimed to have seen things related to these topological effects that should exist in these qubits, but it's all kind of, yeah, not 100% real yet. So topology is a branch of math that describes structures that experience physical changes like being bent or twisted or compacted or stretched, but that still maintain the properties of the original form. And when applied to quantum computing, topological properties create a level of protection that helps the qubit retain information despite what's happening in the environment, which is the very special thing. So topological states protect these qubits in theory. So they should, in principle, have the very longest coherence times. Topological qubits achieve this extra protection in sort of two ways. Way one is called electron fractionalization. Essentially, you're splitting the electron, and this allows quantum information to be stored in both halves, and it kind of gives you some version of data redundancy. If one half of the electron runs into interference, there's still enough information stored in the other half for the computation to go along. The second level of protection that's brought about in these topological qubits is something called ground state degeneracy. So topological qubits are engineered to have two ground states, which is pretty bizarre and unlike most physical systems. And so this makes them much more resistant to environmental noise. So normally achieving this kind of protection isn't feasible because there's no way to discriminate between two ground states. But in topological systems, you can use braiding or measurement to distinguish the difference between the ground states, and that allows them to achieve this additional protection. So, and I hope that somebody chooses to do topological qubits for their class project because it's super fun to learn about, and it's really hard to wrap your head around the concept of braiding and topological states, even from the mathematical sense, is very abstract. The way you want to think about it is that there's a collective state of electrons carrying a charge that's a fraction of the electron charge. So it's not really splitting an electron in half. It's kind of this collective of electrons that is carrying an extra half a charge. That's as good as I can do for right now. That's why these things haven't been discovered yet. On paper, you can write it down. There's ways to make the theory works, but actually finding something in the real world that does this is not happening yet. So it's a very theoretical system. There is a recent demonstration. Azure Quantum, they've engineered a device that allows them to induce a topological state of matter bookended by a pair of what are called Majorana zero modes. Majorana zero modes. They emerge at localized zero energy states at the end of topological superconductors. Those exist. Topological superconductors are a thing. So these Majorana zero modes don't normally exist in nature and have to be coaxed into appearing under very precise conditions. And the ability to create and sustain a quantum phase with a Majorana zero mode and have a measurable topological gap removes kind of the biggest obstacle to realizing this kind of qubit. So this is a Microsoft team that has claimed to have done this. So they've kind of taken the first little step. They've measured something that behaves like they're expecting these to behave in these topological superconductors. Yeah. So this is the foundation for Microsoft's approach to building a quantum computer. And they think this is what's going to set them apart. Other people think they're crazy because, yeah, they're everybody that's working in this area is taking risks. They are taking the most risks. Yeah, and in this whole field, like in all of it, I mean, there's been so many like claims. Oh no, that's not right. Claims, maybe not. And it's because people care so much that people go in and check, and people like really look through. And yeah, I think they have. I think that their observation of the Majorana zero modes is real, but how relevant or useful it is for moving towards a topological qubit may be overstated. I was hoping to do a little bit more of a look at the NV Center. So on your reading quiz, I asked you a little bit about how NV centers store quantum information. And a few people asked about the structure of these NV centers earlier this week. And so I wanted to just show a clearer image of the molecular orbitals, or the electron density in these, the ground and excited state of these qubits. So you can see here the nitrogen vacancy vector is kind of oriented, pointing up here. And what's kind of cool is that in the ground, both the ground and excited state, the majority of the electron density is sitting above the nitrogen, kind of in the plane of those 3 carbons that have the dangling bonds that support the vacancy. And then the electronic structure of these nitrogen vacancy centers we've described a little bit. But when I talked about color centers in insulators or in any semiconductor, you have your valence band and conduction band, and then you have this set of states that are in the gap. So that's just like any color center. But what's special about diamond is kind of the details of the electronic structure. And so, man, I don't have quite enough time to get into it, but I'll just kind of label these things a little bit more than they are. This is a figure from the paper I suggested you read, so it's the review on nitrogen vacancies as sensors. Actually, you know, it's worth, I'll start with this next class, and then we'll start doing math. So next week is our math boot camp. We'll talk about imaginary numbers, and we'll talk about some linear algebra.